This video is going to focus around the concept of something called Le Chatelier principle. The main idea behind Le Chatelier principle can be depicted in this graph that we see on the screen. Okay, it's the representation of that reaction, N2 plus H2 equals NH3, and it's a reversible reaction. What we can see at the start of this graph is that you've achieved equilibrium. And you can tell that because the concentration amounts, right, so it's a graph of concentration, they're constant, they're not changing. So I know I've reached equilibrium. Now at time t, something happens. And if we look at the graph, we can see that at time t, the concentration of N2 spikes up. Okay, what we would call that is a stress. So we have stressed equilibrium by increasing the concentration of N2. The problem is if you increase the concentration of N2, your entire system is going to have to adjust because equilibrium reactions are driven by the value of K, right? K is always the concentration of NH3 squared over the concentration of N2 times concentration of H2 cubed for this reaction. So products over reactants. And K is a constant. So at time t, if I increase N2, so if I increase that variable N2, I will change the value of that K expression, okay? That means I will no longer equal K, and that's a problem because K is what drives equilibrium. So essentially my reaction is going to have to shift. So remember, at equilibrium, my rate of my forward reaction is equaling my rate of my reverse reaction. At time t, because I'm stressing the system, my rate of reaction is going to have to change in order to readjust all the concentrations to get the amounts to equal K again. Because N2 was a reactant, or in the denominator, I'm going to have to decrease production of reactants then, or decrease their amount, and increase my production amount so that I can get that ratio again to equal the value of K. So Le Chatelier principle is about the idea of stress, that I've achieved equilibrium and I'm going to do something to the system to stress it, and the system is going to respond accordingly in order to achieve the equilibrium constant again. So Le Chatelier principle is usually depicted in this way. If a stress is applied to equilibrium, the system is going to shift in order to try to relieve that stress. And what it means to shift is that either it's going to increase the rate of the forward reaction or increase the rate of the reverse reaction in order to do away with whatever stress you've applied. Now, potential stresses on equilibriums are changes in concentrations, which we saw on the last slide, change in temperature, or change in pressure. Something that's not a stress on equilibrium is a catalyst. So if you remember, the addition of a catalyst will speed up the rate. It'll speed it up in both directions. So since I've not adjusted the equilibrium balance of the reactants and products, it's not a stress that will increase the rate in either direction. Okay. The main terms we're going to use with Le Chatelier then are stress. Okay, what have I done to my equilibrium to make it no longer in equilibrium? Right? Did I change my concentration? Did I change my temperature? Did I change my pressure? Second word is shift. So after I apply that stress, how is the reaction going to shift to try to do away with my stress? So it's either going to shift to increase the rate of production of product or increase the rate of production of reactant in order to do away with our stress. So we usually have stress, shift, and then result or effect. So what in the end will the changes in the amounts be in order to basically take in the stress or what's happened? Now, we're going to talk about this really conceptually, but do realize that this is mathematical in nature, in that K is always products over reactants, right? But only at equilibrium. So if my stress increases my amount of product, essentially the shift is going to be shifting to put more reactants in than in order to make K, the numbers get back to K. So that ratio of K can be something you consider in relation to driving at equilibrium. But Le Chatelier principle is all about determining the direction of shift based on the stress applied. So I'm going to show you a simulation of each of the three stresses, concentration, temperature, and pressure, and kind of add some things to it along the way.
Le Chatelier's principle states that if an external stress is applied to a system at equilibrium, the system adjusts in such a way that the stress is partially offset. The word stress means a change in concentration, pressure, volume, or temperature. Fe SCN2+ aqueous, which is red, in equilibrium with iron 3+ ions, which are pale yellow, plus SCN- aqueous, which is colorless, is given by this chemical equation. Click on one of the buttons to add sodium thiocyanate or remove iron 3+ ions from the solution. In this case, the stress applied to the equilibrium system is an increase in the concentration of thiocyanate, SCN-. To offset this stress, some iron 3+ ions react with some of the added thiocyanate ions, and the system shifts from right to left to re-establish equilibrium. When the system shifts to the left, iron thiocyanate ions are produced, which have a red color. Consequently, the red color of the solution deepens as more iron thiocyanate ions, FeSCN2+, are produced.
So with this stress, by increasing the amount of SCN, the sodium doesn't do anything, the Na part, but the SCN we can see is part of the reaction. So if I increase SCN, my reaction wants to shift to undo what I've done. Okay, so if I've increased the amount of a product, I'm going to need to shift to increase my amount of reactant in order to get back to K. So the stress here was an increase in SCN. The shift here was that it shifted towards the reactants or shifted left. And that means that once equilibrium is reestablished, I'm going to have more SCN than I had before. And because it's red in color, I'm going to see that the actual reaction is red in color now. Okay, so the effect then is that I'm going to have an increase of that FSCN ion and a decrease of both the iron and the SCN from where it was at the stress. So stress SCN, shift to the left, increase FeSCN, decrease the other two.
Free iron 3+ ions are removed from the solution. The system shifts from left to right to replace some of the iron 3+ ions. As the system shifts to the right, the concentration of iron thiocyanate ions, FeSCN2+, decreases. The red solution turns yellow due to the decrease in concentration of the red iron thiocyanate, FeSCN2+ ions, and the formation of the yellow iron 3 ions. Consider the equilibrium between iodine gas molecules, I2, and iodine atoms at high temperature. Iodine molecules in the gas phase are a purple color, and iodine atoms are colorless. Let's stress this system by changing the pressure. Click on one of the pressure buttons. You have increased the pressure by decreasing the volume of the container. The system can partially offset this stress by decreasing the moles of gas. Recall that pressure is directly proportional to the moles of gas. Because of the 2-to-1 mole ratio in the balanced equation, the moles of gas can be decreased if the system shifts to the left, producing iodine molecules and decreasing the number of iodine atoms, as you can see in the microscopic view. Note that the total number of gas particles has decreased. As more iodine molecules, which have a purple color, are produced, the color of the equilibrium mixture darkens.
So in this example of increasing pressure, pressure is one of the harder concepts for most people. So pressure only affects systems that have an unequal number of gases. If you change pressure on like an aqueous environment or change pressure where the gases are equal on both sides, you can't shift equilibrium to adjust to this. But in this particular case, if you increase pressure, again, Le Chatelier says the system wants to shift to try to undo what I've done. So if I've increased pressure by decreasing volume, I want to shift to make less stuff, because back in gas laws we learned less stuff means less pressure. So if I look at this equation, on one side I just have I2, so one I2, and on the other side I have two I's. So technically the side with two I's has more things, so if we shift to the side of 2I, we'll make more pressure. So in this case, because the stress was I've externally put more pressure on the system, now I'm going to shift to try to decrease the pressure and relieve it. That's why we shift left. That's why we see an increase in I2, And again, because it's purple in nature, you'll see the color shift to being a darker purple.
You have decreased the pressure by increasing the volume of the container. Le Chatelier's principle states that this stress will be partially offset. The system can partially offset this stress by increasing the moles of gas. Pressure is directly proportional to the moles of gas. Because of the 2-to-1 mole ratio in the balanced equation, more moles of gas can be produced if the system shifts to the right, producing more iodine atoms, as you can see in the microscopic view. As more iodine atoms, which is a colorless gas, are produced, the color of the equilibrium mixture lightens, as you can see in the macroscopic view. Consider the following reaction at equilibrium. N2O4 in equilibrium with nitrogen dioxide, NO2. Because NO2 is a brown gas, the equilibrium mixture has a brown color, as shown in the macroscopic view. Let's stress this system by changing the temperature. Click to select either increased temperature or decreased temperature. You have increased the temperature of the system by adding heat. Le Chatelier's principle states that this stress will be partially offset. This reaction is endothermic, so you can think of heat as a reactant. Heat must be supplied to the reacting mixture. The system can partially remove the added heat by shifting to the right, producing more NO2 and decreasing N2O4, as you can see in the microscopic view. As more NO2, a brown gas, is produced, the color of the equilibrium mixture darkens, as you can see in the macroscopic view. You have decreased the temperature of the system by removing heat. This reaction is endothermic, so you can think of heat as a reactant. Heat must be supplied to the reacting mixture. The system can replace some of the heat that was removed by shifting to the left, producing more N2O4 and decreasing NO2, as you can see in the microscopic view. As more N2O4, a colorless gas, is produced, the color of the equilibrium mixture becomes lighter, as you can see in the macroscopic view.
That's it for your intro video on Le Chatelier. I know it's long. You definitely, for the worksheet, want to walk through each of these simulations and talk about what is the stress, right? Like, is it an increased temp, decreased temp, increased pressure, decreased pressure? Am I adding something or removing something? What is the shift? And it'll always be shift left or shift right. Or you could say shift towards reaction, shift towards product. Then the effect is wherever you essentially are shifting towards, that stuff is going to go up, and wherever you shifted away from, that stuff's going to go down. So if you shift left towards the reactants, that means you'll make more reactants and make less product. If instead you shift right, you'll make more product and make less reactants. Next step will be a video with me doing demos. Same thing. You'll do a lab with this. Same thing. We beat Le Chatelier to death. It's not that hard, but for some reason it's very confusing for people. So lots and 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 lots of practice. That's it. Have a nice night.